Consider a circuit consisting of an independent voltage source and a resistor that are connected in series. If we connect a load resistance that we'll call RL across the terminals A and B, we can see that the current passing through this load resistor, we'll call IL, will have a value of Vs over R plus RL. That's the total voltage divided by the total resistance in the circuit. We can also see that the voltage across that load, VL, we'll say, is going to be Vs times RL divided by R plus RL. You can either think of this as a voltage divider, or you can think of this as the current multiplied by the resistance would give us the voltage. Now let's suppose instead that we have a circuit consisting of an independent current source and a resistor that are connected in parallel with one another. Following the same idea as before, let's imagine we have a load resistance RL connected at terminals A and B. In that case, the current flowing through that load resistance IL will be IS, the source current, times R divided by R plus RL. In this case, this is a current divider. The voltage across RL, which again we'll call VL, will either be the current multiplied by the resistance, or you can see that this is the current times the equivalent resistance of two resistors in parallel. Now let us consider and compare these two results. We've found expressions for the load current and the load voltage for a resistive load RL connected to a voltage source, and we found similar expressions for the current and load voltages for a circuit with a independent current source in parallel with our resistor and our load resistance. Notice the similarities between the load currents and the load voltages for this same arbitrary load resistance. We can see that these expressions, both of them, are going to be exactly the same if and only if Vs is equal to Is times R, or again here Vs is Is times R. If this relationship is met, then we have the exact same current and the exact same voltage being applied to some arbitrary load, regardless of whether we have a voltage source in series with a resistor or a current source in parallel with a resistor. Thus, these two sources are equivalent to one another, assuming we use this transformation. This means that if you find an independent voltage source in series with a resistor in your circuit, you can remove that circuit at its terminals, and you can replace it with a current source in parallel with a resistor connected to the same terminals, assuming that you keep the same resistance R and you transform the voltage source into a current source with the proper value. This same idea is true going the opposite way. If you have a current source in parallel with a resistor, you can convert that to a voltage source in series with a resistor, again using the proper conversion to keep the circuit equivalent, but perhaps simpler. Sometimes circuits are a little bit more complicated. For example, there might be a parallel resistor RP that is in parallel with a voltage source. In this case, the voltage source has to supply a current to that parallel resistor, as well as applying a current that is going to go through that series resistor and into the load that's connected across terminals A and B. In this situation, the voltage source is indeed applying a voltage to that parallel resistor and driving a current through that parallel resistor, but all of that is happening inside the overall circuit. Nothing that's going on here is going to affect what's going on outside these circuits at those terminals A and B. Thus, if you see a resistor in parallel with your voltage source, you can simply omit it and treat it as this simpler circuit. However, the existence of this parallel resistor means that the voltage source is driving more current through it, and this will reduce the efficiency of the circuit because the voltage source is putting in energy to drive that current, but it's not changing the overall equivalent behavior if we are simply looking for simplicity. Similarly, we may find that there is a series resistor, RS, that is in series with a current source, and then that series is in parallel with a resistor and with a load that would be connected to terminals A and B. In this case, our current source would have to drive the source current through that series resistor and then that current would end up splitting off, and some of it would go to the load, as we've seen before. In this case, all of the current from the current source is going to make it through that series resistor. There's nowhere else for it to go. And then that same current that we've seen is going to branch off through the parallel resistance and through the load, as we've seen as well. So the same current is going to be delivered to the load as there was before. Thus, we can ignore this series resistor, and we can use a simpler equivalent circuit in this case. We know that the current is going to be delivered to the load the way it was before, and so whether that series resistor is there or not isn't going to affect what's going on outside the circuit beyond the terminals A and B. However, we're going to have a load voltage at the terminals, but now we'll also have a voltage drop across this series resistor. What this is going to do is going to increase the voltage across the current source compared to the voltage across the current source in the simpler circuit. Again, this doesn't affect the outside of the circuit, and for simple calculations, you can go straight with the simpler circuit. But this current source is operating now at a higher potential, and thus is going to require more energy. And again, this series resistor is going to reduce the overall efficiency of the circuit, even if it isn't going to affect the overall behavior.